Can you create a second scene with full screen camera?
Okay, we're good.
Okay, yeah, just select the background.
Okay. Can you check the Bluetooth? Just make sure the volume is good.
Three wires here that are maybe 100 yards long. This probably has 10 miles of wire. Systems, subsystems. That's what one of the wires we're trying to use was. There's a big one. What's new, Bob? Are you want me to tell jokes?
Jeez, this computer.
OBS? Stop. Stop. Maybe we should start with questions.
Well, if there's any inaccuracy in this opening slide, I'm going to hear about it. Because
I guess everyone's been
right.
watching
Like
it.
if I didn't get that rectangle put on the right spot. Dave Premier. All right,
No.
thumbs up.
Oh, thumbs up.
Okay.
All right, we are good to go. Thank you so much. All right, I'm just going to do a brief introduction. We have our Vice Dean of Research, Deanna Barch, coming up, who will welcome everyone to the WashU campus, virtually and in person.
Great. Hello, everybody, and welcome to our beautiful Graham Chapel for those in person, and welcome online to the St. Louis science community and hopefully a broader science community. It is my great pleasure to welcome you all here on the part of Dean Feng-Sheng Hu, our Dean of Arts and Sciences, who is currently out of the country. This is such an important and exciting lecture, and we feel very honored to be able to support Dr. Canup's presentation tonight. As some of you may know, but many may not, WashU has a long-standing commitment and dedication to support cutting-edge research on space sciences, including having established the McDonald Center for Space Sciences. Tonight's lecture is a part of that important focus on understanding the frontiers of space and the formation and evolution of the solar system, the galaxy, and the universe. This probably is more important than ever these days. We hope you find this lecture thought-provoking and informative, and I want to take a moment to thank Dr. Jeff Gillis-Davis for his leadership in helping to organize this, as well as Dr. Brad Joliffe, the director of the McDonald Center for Space Sciences, and in particular, thank Dr. Canup for taking her precious time to come and tell us about the origins of the moon.
This is so important that we get to have multiple introductions. So welcome all of you, those of you who are in the room and those of you who are online. And if you're in the room and you're from St. Louis, you look around you, you may find lots of planetary scientists embedded and students of planetary science. We're very fortunate to have the meeting, the NASA Exploration Science Forum meeting here at Washington University this week, today, tomorrow, and Thursday. And this is organized and run annually by the Solar System Exploration Research Virtual Institute. And the director, Greg Schmidt, I want to recognize Greg. Thank you very much, Greg. You and the members of Survey Central are absolutely phenomenal in pulling off this meeting every year. And we're just pleased to have it here at Washington University. And also to Jeff for having the determination to say, let's have the meeting in St. Louis. So it's great. And it's fitting, we're going to talk a lot about the moon, and at Washington University we've been studying the moon for, well, 50 years or more, going back to the early Apollo days and the days of Bob Walker, who was first looking at cosmic rays and solar-wind interaction with the surface, noble gases, space weathering, and 50 years later, Dr. Gillis-Davis is doing this in his laboratory now where he simulates these effects. And in the meantime, we've had many good years of studying Apollo samples, Apollo meteorites. I was fortunate enough to come here to work with Dr. Larry Haskin, who passed a number of years back, and the recently retired Randy Korotev. We've looked at thousands of lunar samples. We love lunar rocks, breccias, regolith, you name it. We've analyzed it. And then transitioning to remote sensing, involvement with the Clementine mission. Jeff was involved with that, Lunar Prospector, Lunar Reconnaissance Orbiter, and looking forward to Artemis 3, next human mission to the surface of the moon. So lots going on, and we've been very fortunate to be a part of it. Speaking of the moon, some 3 decades or a little more ago, the hypothesis came up, this was well after Apollo, that perhaps the moon formed by impact of a large impactor into the early Earth. Hypothesis at the time, but tonight's speaker is going to tell us more about that. But let me say a little bit words of introduction for tonight's speaker, Dr. Robin Canup. She got her undergraduate degree at Duke University in North Carolina, PhD in astrophysics, planetary and atmospheric sciences at the University of Colorado. She then spent a few years working with LASP there in Colorado before going over to the Southwest Research Institute, SWIRI in Boulder. Since then, in addition to being a phenomenal scientist, she's held about every position of responsibility that you can hold at Southwest Research Institute, including Institute Scientist, Vice President, Associate Vice President, and now Vice President for the Planetary Science and Exploration Division of Southwest Research Institute. So she's done a tremendous amount there. But speaking of great things, because of this, she has many accolades, too many for me to mention, but I'll just mention a few. Going back to about the time of the early work on the origin of the moon, she received the Harold C. Urey Award of the AAS. That's the highest honor you can receive from that organization. She was elected to the National Academy of Sciences and the American Academy of Arts and Sciences. So very highly decorated. And as a result of that, NASA and the National Academy asked her to be the co-chair of the last Planetary Science Decadal Survey. This is about 5 years ago, right? 5 years ago, 4 to 5 years ago. This is a big deal. There are literally hundreds of scientists and a whole community of scientists involved in this organization, and she led it, and it's like herding hundreds of cats. And she did it beautifully, and it's a big deal because it lays out the priorities for solar system exploration for NASA for the next decade. And she's still here to talk about it, and she survived it, let's say. So going back to the moon, so what about the moon? We had this hypothesis some 3 decades ago that the moon formed by giant impact into early Earth. Well, with Robin's early studies, she looked into this in detail and then did the computer simulations that really took this from being a hypothesis to being a theory. And in fact, it's now the leading theory for the origin of the moon. She is going to tell us more about this, and again, we're very appreciative of you all coming, but we're appreciative of her being here to talk about the origin of the moon. So, Robin.
Thank you so much. It is a pleasure to be here in this stunning venue, so thank you very much. Surely the origin of the moon is one of the oldest questions in planetary science. People have looked up in the sky and wondered, how did our companion get there? The moon is, of course, a very fascinating planetary object in its own right, but its importance and the importance of understanding how it formed is enhanced because of its close relationship to our planet Earth. The moon has been our companion throughout our history. It has always affected and continues to affect our planet. On Earth, our active geology has largely erased the direct evidence of our planet's formation and very early processes. But the moon is much more ancient, and it preserves the record of primordial events. And because of that, studying the moon allows us to obtain some of the best constraints on how our planet formed. And then understanding how our Earth-Moon system formed is a way to teach us about how solid planets form around stars and then better understand the likelihood of Earth-like planets around other stars. I'll start by talking about what we understand about the formation of interterrestrial planets. Then I'll talk about the giant impact theory and what has been referred to as the isotopic crisis for the impact theory that comes from detailed analysis of Apollo samples, as well as proposed solutions to this crisis. And I'll finish by talking about key needed data to make further progress and optimism that we're actually going to be able to get this data in the near term, thanks to a renaissance in the exploration of the moon. It's been appreciated for centuries that planets form from disk orbiting young stars. These disks, primarily of hydrogen and helium gas, but also with 1% or 2% of their mass in tiny grains of dust, are a natural byproduct of the same collapse process that leads to the formation of a star. Now, for decades, and certainly when I started as a planetary scientist, we could only use theoretical models and maybe computer simulations to study these disks. But now we actually have phenomenal observing facilities that are capable of directly observing these disks around many young stars. And shown on the right is a now very famous picture of the protoplanetary disk around HL Tau, a less than 1 million year old star. And you can see amazing structure in the disk. And this is an example of a system that we think we can observe in the process of forming planets. So tremendous advances in this field overall being brought about by these observations of young stellar objects and their disk. So in our solar system, we know that the end product of planet formation was our 8 primary planets. The outer 4 grew massive enough to gravitationally capture some of that hydrogen and helium gas from the protoplanetary disk. But the inner 4 planets did not, so they remained solid rather than gaseous. We refer to the inner 4 planets as the terrestrial planets. And of these 4, Mercury, Venus, Earth, and Mars, it's only the Earth that has a large moon. How do we think the terrestrial planets formed? So initially there was this protoplanetary disk of primarily gas and dust grains. Initially the grains would have been very strongly aerodynamically coupled to the gas and flow along with it in orbit around the star. And so when grains collided with each other, they would do so very gently, leading to sticky collisions and the growth of centimeter-scale pebbles. At that point, the relative speeds of collisions between the objects would have been large enough to prevent their further growth due to those binary collisions. So we think what happens next is that there are certain types of interactions with the gas disk that cause large regions of these pebbles to be concentrated to such an extent that a whole collection of pebbles will collapse due to its own self-gravity to form a much larger 100-kilometer scale object that we call a planetesimal. Once large planetesimals form, then once again, their two-body collisions can lead to mergers, now due to their own mutual gravity, leading to a merged object after the collision. So as the planetesimals collide, they form increasingly larger objects, protoplanets that are Moon to Mars sized. And then there's a final phase involving giant collisions between these protoplanets. It's like a process of elimination. The planets continue colliding until, and reducing their number through merging, until the final planets are on well-spaced out enough orbits that they no longer collide. On the right, I'm going to show you a simulation of what I've called phase 3 and phase 4 that considers an initial distribution of protoplanets and planetesimals in the inner disk in the region where the terrestrial planets are, as well as a Jupiter out here and an asteroid belt in between. So the simulation is actually called an n-body simulation. It's tracking the orbits of all of these particles as they go around the star explicitly. And every time they collide, it assumes that they merge. But in this plot, we're just looking at the distance from the sun on the x-axis and then the orbital eccentricity on the vertical axis. So that's a function of how non-circular or elongated the orbit is. What you'll see is that growth in the inner disk proceeds very quickly, and within even 1 million years, relatively large protoplanets have formed. So quite quickly, 5 protoplanets have formed in the inner solar system, and then at about 40 million years, there's a final giant impact that leaves 4 inner planets. Of course, we're highlighting the one that yields a really good match to our solar system. But this is a stochastic process, and this is an example of one that yields a good solar system analog. How do we think the Earth-Moon system formed in the context of this overall view? Let's start by talking about 2 properties of the moon that any theory for its origin has to explain. The first relates to its bulk composition. We know from its low density, which we can get just from the size of the moon and its mass, that the moon is depleted in metallic iron. By mass, it must contain about less than 10% of its mass in iron. This is much less than, say, the case for the Earth, where the iron-dominated metallic core is about 30% of the Earth's mass. So whatever process formed the moon selected against the incorporation of metallic iron. The other remarkable thing about the moon is that its orbit has evolved hugely over its history, and this is due to tidal interaction between the Earth and the moon. The moon's gravity on the Earth tends to distort the shape of the Earth, and this is seen most easily in the Earth's ocean, and this is the effect that twice daily high tides. The shape of the Earth in response to the moon's gravity doesn't form instantaneously, and then in the time it takes these tidal bulges to reach their equilibrium figure, Because the Earth's angular speed of rotation is faster than the moon's angular velocity around the Earth, the day is shorter than the month, the equilibrium tidal bulge forms ahead of the moon by a little bit. And it's always in this position, where it's slightly ahead of the moon. And the gravitational interaction between this tidal bulge and the moon leads to a positive acceleration in the direction of the moon's orbit, which leads to a positive torque on the moon's orbit that causes its orbit to expand, and there's an equal and opposite torque on the Earth's rotation that causes the rotation to slow. And this whole process conserves angular momentum. So what that means is that since we know the moon's orbit has been expanding over time, we can take its current position at 60 Earth radii away and our current 24-hour day and go backwards in time to when the moon was very close to the Earth when it formed, to deduce that the Earth was then rotating much more rapidly with only about a 5-hour day. So as Brad mentioned, the giant impact theory is currently the leading idea for how the moon formed. The idea was originally proposed as one of the scientific byproducts of the Apollo program. The concept is that during one of those large collisions between protoplanets, ejecta went into orbit around the Earth, and it was from that disk around the Earth that the moon then accumulated. Now, initially, the theory was viewed with a lot of skepticism, I would say. The concern was that if you consider a spherical planet and a ballistic trajectory from its surface, then something will either re-impact the Earth or escape. It won't go into orbit around the Earth. And so it was thought that maybe it would have to be an extremely unusual type of event to form a disk at all, and could it be massive enough to form our large moon? The challenge in addressing this was that, of course, we can't simulate two planets colliding in the laboratory. So in order to really see whether this mechanism could work, we had to devise computer simulations that were capable of modeling with the physics accurately included what happens when planets collide. And I'll mention that it's become very customary to call the impacting planet that we think led to the moon, to give it the name Theia, the mother of the moon. I'm going to be showing you simulations that use a method called smooth particle hydrodynamics. In this method, both Theia and the proto-Earth, shown here in the early stage of a collision, are represented by a large number of individual particles, and each particle has a fixed mass and a fixed composition. The composition in these simulations is either a silicate mantle particle or an iron core particle. Very simplistic treatment in that sense. Then the code tracks the evolution of the dynamic variables, the position and velocity, as well as the thermodynamic state of all the particles, the temperature and the phase, whether it's melt or vapor or a mixture of the two. As the system evolves due to mutual gravitational interactions between all these particles, pressure forces, and shock dissipation. Okay, so I'm going to show you a simulation of the impact of a Mars-sized Theia at a 45-degree impact angle, and this has come to be known as a canonical moon-forming impact. So what you'll see is the impact coming in from the upper right. The color scheme here, blue corresponds to molten rock, red is fully vaporized rock. And so you'll see immediately the scale of this event, what it does to the shape of the Earth, how the Earth is so distorted that my picture that I described of a bullet being fired from the surface of a spherical planet as landing or escaping doesn't hold. The planet isn't spherical after this type of event. Okay, so here we go. Oops. Let's see. There's the initial collision. You can see the shock wave going around the Earth. There's a re-collision that occurs right now of a large piece of Theia. The red is silicate vapor produced from the initial shock of the impact that's wrapped itself around the Earth. We're now looking at the system in the equatorial plane of the impact. You can see the Earth is very oblate. It's because it's rotating with about a 5-hour day. There's a large intact piece of the impacting planet that passes close to the Earth and is sheared apart that we saw just then. In all, the simulation is tracking about 24 hours of time, and at the end of the simulation, you can add up the mass and the momentum of the material in orbit around the planet and conclude that there's enough material there to later accumulate into a moon of the right mass. Okay, let's start with the iron. This is the same impact, but a much less impressive animation, because this one is just a 2D slice so that you can see the behavior of the iron. So the iron here is in red, and I've assumed that Theia initially had a large iron core just like the Earth did. So viewed in this color scheme, you can see that that initial re-impact is actually almost entirely made up of the iron core from Theia. So when that large secondary impact occurs, almost all the iron from Theia is removed from the pre-lunar disk. And in the end, the disk has only a few percent, at most, iron by mass. And so we find these giant oblique impacts by a Theia that's already differentiated to be a natural way to explain why the moon's depleted in iron. Here's another interesting thing you can do with this type of data. Same simulation, only now we're starting with the end condition and we're going to run it backwards. And here the color scheme tells us the fate of each of the particles. The yellow particles are the ones that end up in the disk from which the moon will eventually form. The blue particles are those that are accreted by the Earth, and the red particles are those that escape. So we're going to keep that color mapping on each particle and run the simulation backwards. And this allows us to see where the material that ends up in the disk came from. And when you do this, what you find is that the disk material is derived overwhelmingly from a leading region on the impacting planet. That's the material that is most effectively torqued into orbit by that initial distortion of the shape of the Earth produced by the impact. So these simulations are 20 years old, and their resolutions are quite low by modern standards. And in the past 20 years, there have now been thousands of impact simulations conducted. This particular one I'm showing here is about a factor of 100 higher resolution, and it has been rendered in a way to hopefully more realistically depict the phase and temperature information that the code is producing for each of the particles, and to add in the background stars. That's just artistic license. But here, the hottest material is the white hot, and the red-orange material is molten material. So many different groups around the world have done simulations like this and varied the mass of Theia and the angle and the impact speed and even the initial rotation state of both objects before the collision. We've even modeled these impacts with completely different types of hydrodynamic methods that use a grid code rather than a particle-based code. And so we think we have a very good understanding of the outcome of these giant impacts. One of the surprising results is that most of these giant impacts that occur at relatively low velocities also produce moons. The moons may have different masses relative to the planet, but moon outcome has turned out to be a very common result of these large collisions that we think were a part of forming an Earth-sized planet. With respect to the particular class of impacts that produces a disk massive enough to produce our moon, which is quite big, in nearly all cases, the disk is derived primarily from Theia rather than from the proto-Earth. And that's due to the importance of the gravitational torques getting that material into orbit, and the material from Theia, in almost all cases, is more effectively placed into orbit. One other thing I'll point out about this before we move on, because it'll relate to a later slide, is that this outcome of a highly heated rock vapor atmosphere, this is not a normal atmosphere around the planet. Again, this is a vaporized rock atmosphere, and an inner disk that is also very hot in combination with an outer disk that is mostly molten material, and you can see it's already clumping and forming little moonlets. So we'll return to that. So the canonical impact explains the main properties that I've talked about so far really well. It gives us the mass of the Earth and the Moon. It gives us the Moon's iron depletion. It's the most obvious explanation for the Earth's rapid initial rotation rate that eventually gave us our 24-hour day. So I like to say that if this were a typical problem in astrophysics, where everything we know about an object is due to looking at it remotely from a distance, we would have thought we had this all understood and we would have stopped working on it decades ago and moved on. Everything I'm going to talk about for the rest of the talk is because we have samples from the Moon. And it's the analysis of those samples and their detailed relationship to Earth rocks that tells us that the simple picture I've described so far is missing something. So let me talk about that. We can compare rocks from the Moon with rocks from the Earth's mantle, and in particular, we can compare their isotopic compositions across different elements. And what we find across all elements that are not volatile is that the Earth and Moon have essentially the same isotopic composition across all these elements. And in contrast, meteorites from Mars or from the asteroid belt have very different composition. So to give an example, the most frequently cited case is oxygen with 3 stable isotopes. O16 is standard oxygen, O17, 1 extra neutron, O18, 2 extra neutrons. So if you look at the ratio of O17 to O16 and O18 to O16 in a sample from an Earth cloud versus a sample from the ocean, they'll fall at different places on this plot, but all of them will fall on a single line on this plot, and that's because planetary processes that change the relative proportion of isotopes do so in a way that varies with isotope mass. So that if a process changes the relative amount of O17 to O16, it'll change the amount of O18 to O16 by twice as much, because the difference between O18 and O16 is twice as big as the difference between O17 and O16. Okay. We look at meteorites from Mars, they also fall along their own line, but that line is offset from that of the Earth by a lot. So this line here being offset from that of the Earth, it suggests this is a completely independent reservoir of initial isotopic composition from which Mars formed that was different from that of the Earth. Okay. But the Moon samples, the lunar samples, interestingly, fall entirely on the Earth fractionation line. And we knew this from Apollo, but there were uncertainties. And as these ratios have been measured with more and more precision, the size of the potential difference between the Earth and Moon has gotten really small. So what's the problem? The problem is, as we've seen, almost all giant impacts produce the disk from which the Moon would form from the impacting planet, which would have had its own separate formation history. Well, if that planet was as isotopically different from Earth as we know Mars is, then we would expect that the Moon would be measurably isotopically different than the Earth. But instead, they're identical. So that's the isotopic crisis. How do we merge these two objects formed completely separately, mix up their material, and yet end up with two isotopically identical objects? There are several ideas for how to accomplish this. Perhaps the simplest is, well, what if Theia was just isotopically like the Earth? It's thought that for elements like oxygen, the isotopic composition reflects local conditions in the protoplanetary disk. And so if Theia accreted from the same feeding zone in the disk as Earth did, then it might have had the same composition. And we can estimate how likely this is by using the same types of n-body simulations that I showed in the planet accretion simulation earlier. And so, for example, in this work, they're showing that in about 20% of cases, the final large impactor onto the Earth analog planet is isotopically similar to that Earth analog, while at the same time, the planet that forms next in line is isotopically different. Okay, that seems like a great explanation. And we thought that was the whole story for a while, until it was understood that the Earth and Moon also have identical isotopic compositions in an element that cannot be explained in this way, and that element's tungsten. And it turns out, and I won't go into this in detail, that's a really interesting other talk, that an object's tungsten isotopic composition reflects not where it formed in the protostellar disk, but the timing of when its metallic core formed. And so requiring both that Theia formed near to the Earth and that the core in Theia and the core in the proto-Earth happened to form at the same time to explain tungsten 2, the probability of those two low probability events seems really unlikely. Another idea. You saw that these impacts produce vapor. What if mixing between the vapor component of the Earth and the disk mixed and equilibrated their compositions before the Moon formed? So you essentially erase the composition, or you erase the signature of Theia in the disk and contaminate it with Earth's composition. Here the key question is, could you really have this much mixing before the Moon accumulates? So let's talk about this one a little more. So I pointed out that picture at the end of the simulation where you have the hot inner disk, but then the outer regions of the disk are already starting to accumulate. And that's a typical outcome after a canonical impact. And so I'm going to show you some quite simplified models of how the Moon is assembled from such a disk. The bottom image shows that there are two main regimes in this disk around the Earth. In the outer disk, the material is largely condensed, and you'll see the Moon can accrete very quickly from whatever material is out there. The inner disk is hotter and interior to a distance known as the Roche limit, which is at about 3 Earth radii from the center of the Earth. Earth's gravity keeps material from being able to accumulate and grow into large moons. It's inside the Roche limit at Saturn, for example, that we see Saturn's rings. So in the protolunar disk, inside this Roche limit, the disk is cooling, and the melt layer is clumping and getting sheared apart by tides, and that dissipates energy. It keeps it hot for longer, and it also causes the inner disk to radially spread inward and outward. Here's a simplified construct to try to capture that situation. Here, the inner disk is just represented by this orange bar. We're just tracking its mass and assuming it's a uniform slab, and we're following the accumulation of moonlets outside the Roche limit. And what you see is within a month, everything outside the Roche limit that is molten accumulates into a large moonlet. The inner disk takes decades before it cools enough and starts to spread material out so it can get accreted by the Moon. And the material from the inner disk that's being added to the Moon is represented in this simulation as an orange layer. In these models, there's a typical pattern whereby this is a plot of the mass of the Moon versus time. The initial phase of growth, in this case of about 40% of the Moon's mass, extraordinarily rapid, only in a month. Then there's a period where there's a stall as the inner disk cools, and maybe during this period, the inner disk is able to mix with the Earth and equilibrate isotopically. At least that's the idea. And then eventually, the inner disk material, in this case, the last 60% of the Earth's mass, is then accreted onto the Moon. Well, in this construct, unless mixing within the Moon after it forms is complete, you might think that you could have preserved a heterogeneous compositional distribution in the Moon's interior, with the inner part of the Moon that rapidly formed most likely to retain the isotopic signature from Theia, and the last added layer on the outside of the Moon, the most likely to have equilibrated the Earth and to be isotopically Earth-like. And of course, our samples are strongly biased to tell us about the outer crustal layers. There are some hints in our current sample set, that as you go to samples that were sourced more deeply, they look more isotopically different than the Earth, but we really have very few samples that reflect the deep interior to make a firm conclusion, I would say. The final possibility is that the moon formed by one of a very special class of impacts that does produce a disk and an Earth with the same mix of material. This collision is known as the half-Earth impact. In this case, both Theia and the Earth are similar in mass and each has about half the mass of the current Earth. And because of the symmetry in this collision, in the end, both the disk and the planet are each comprised of roughly half of their material from Theia and half from the proto-Earth, so their relative compositions can be essentially equal. This is a much higher energy, much higher angular momentum event than the canonical impact. It leads to a completely vaporized disk, a largely vaporized structure for the Earth, and a co-rotating inner structure that has been referred to as a synestia. And this is one of a class of impacts that produces such a structure. These impacts, however, leave the Earth-Moon system with excess angular momentum, with an Earth that's rotating too quickly, with an Earth with a day of only 2 to 3 hours. And so they require some dynamical mechanism after the fact to slow down the Earth's rotation by a factor of 2. That's a big deal. But believe it or not, there actually are a couple resonant interactions involving the Sun, the Earth, and the Moon, the three-body system, that may be capable of doing this, but so far we haven't been able to determine how probable they are, because they depend sensitively on the nature of tidal interaction during this early Earth-Moon history. Okay, where does that leave us? As I mentioned, it's now clear that the same impacts that we need to build these planets will also be frequent producers of moons all throughout planet formation. Many moons may be lost, of course, but this should be a very efficient process for forming them. However, explaining the specific properties of our Earth-Moon system, the combination of the isotopic similarity, the mass of the moon, the angular momentum, has proven to be very challenging. I talked about 3 possible solutions to the so-called isotopic crisis, but I'd like to point out that our understanding of the isotopic crisis itself is influenced by the samples we have in our collection, which largely sample the lunar crust, and we lack samples from the moon's mantle, for example. So how do we make progress? How do we unravel this picture and firmly understand the nature of the event that produced our Earth-Moon system? I would argue that samples from the lunar far side will provide key data that will help us do this. The Apollo mission sampled only the younger near side. The far side, shown on the right by comparison, is more ancient, and it also hosts the largest impact basin on the moon, the South Pole Aitken Basin, shown approximately by this white dotted circle there. Now the SPA basin, why is that interesting? It's so big that when we do hydrodynamical simulations of the formation of the SPA basin, we predict that it should have excavated material at least from the deep crust, if not from the mantle of the moon, and brought that material up to the surface of the moon where we should be able to sample it. And of course, if we could sample it, then that would tell us whether or not that material looked isotopically different from the Earth and retains the signature of our hypothesized Theia. Furthermore, on the far side, dating the age of the earliest basins on the moon constrains the nature of terrestrial planet accretion and the timing of that, and that in turn constrains our ideas about the likelihood of having an isotopically Earth-like Theia, that first possible solution. So it's with great enthusiasm, after having given some flavor of this talk for many, many years, that I say that I think we're actually going to get this data in the next 5 to 10 years. There has been an extraordinary rebirth of lunar exploration, both in putting robotic and instrument packages on the surface of the moon, and also the Artemis program, which will return humans to the moon in the next few years. And all of these efforts are going to teach us more about the moon, return samples, particularly from the far side. But I want to end by advertising a particular mission that the decadal survey that Brad mentioned prioritized for the next decade in lunar research. The Endurance A mission envisions a robotic lunar rover that would conduct a very long 2,000-kilometer traverse within SPA Basin on the lunar far side. This is an example trajectory, traverse for the rover. It would actually go the other way. And this trajectory would be chosen so as to visit the key spots for the samples needed to hopefully discover deep crust or mantle samples, to date SPA, and to date the largest basins superimposed on SPA, and to also understand just the earliest generation or the earliest geological evolution of the moon in general. The rover would bring these samples back to the Artemis South Pole Base Camp and leave them for study and ultimate return to the Earth by the Artemis astronauts. So this was envisioned to be what we see to be a groundbreaking collaboration between the human exploration and robotic scientific exploration sides of NASA to truly revolutionize our understanding not just of Earth-Moon origin, but also of the moon itself, and beyond that, to return an Apollo-class sample set from across the far side of the moon to the benefit of all future generations. Because just look, I'm giving this talk and I'm telling you everything interesting about this problem is based on these samples that we brought back more than 50 years ago. Let's give the next generation samples from the far side of the moon so that they can have another 50 years of great discoveries. Thank you.
Thank you very much, Robin. That's an amazing, amazing set of discoveries and advancements of the theory over the past 20 years. I failed to mention at the beginning that when she was an undergraduate, she was a physics major. Was that obvious? Yeah. And she's also done quite well with the cosmochemistry. And indeed, we continue to try to test the theory with all kinds of different isotope systems, and it'll keep us busy for a long time, and we really need those samples from South Polakin. We have time for some questions.
Questions. We'll do the general public first. Oh, we got one in the back. We'll use the mic because there are people online.
How do we know, and what is the evidence that the far side of the moon is so much more ancient than the near side?
So the simplest answer is the main way that we determine the relative age of surfaces is by computing the density of craters on the surface. So the older a surface is, the longer it's been exposed to meteoroid impact, the more craters, the denser the craters will be on its surface. So if you just compare the near side of the moon on the left, of course, this is where we see the mare, the volcanic flows that have presumably flowed in and covered a more ancient region underneath, versus the far side of the moon on the right, that is more heavily cratered. And there are, there's a lack of recent geological processes that we see, but at the simplest level, that's the answer to the question.
Why wasn't a theory where the moon breaks off from the Earth considered? Because then you'd have the similar composition of the Earth on the moon.
I'm so sorry, I missed the first half sentence.
Was there a theory that was considered where the Earth, where the moon split off from the Earth like a fission?
Right. And actually, believe it or not, these high angular momentum impacts are essentially impact-induced fission. That's another way to think about them. So, as I mentioned, this half-Earth impact, this is one of a range of high angular momentum impacts that can produce a disk with the composition of the Earth. But there's also an impact in which you have a much smaller impact that hits into the Earth that's already rotating at almost the instability speed, and it's collisionally induced fission. And it produces an Earth composition disk in that way. So you're exactly right. So that fission idea, of course, dates all the way back to one of the Darwins. But interestingly, these high angular momentum impacts, they bear a resemblance to that, indeed.
You mentioned that you reversed the time based on the tides being ahead of the Earth's orbit to kind of go back in time and see how close the moon was and deduce the rotation speed of the Earth. And you went back to 5 hours because that was the limit of where the material could be in a disk. And I don't remember the name of that line, but how can you be sure that the moon formed like at the border of that line at 5 hours, and it wasn't like 6 hours or 7 hours, and it just, like a big chunk was more to the right of that line?
Sure, that's a great question. So the name of that line is called the Roche limit. You have a very good memory. And indeed, the 5-hour day is the answer you get when you put the moon just outside of that line. But it could have formed, and indeed the simulations often have it forming, somewhat beyond that line. So what really matters when we ask ourselves, when we have the results from a simulation, is this a successful outcome? We don't check the length of the day of the Earth. What we do is we check the total angular momentum of the bound system, because that's the key constraint. Because then, as long as that's consistent with the 24-hour day and where the Earth moon is, then it can put us anywhere along that continuum of having the moon form slightly beyond the Roche limit with the Earth with a slightly reduced rotation rate. Did that make sense?
Because the argument was that you would get extruded material, basically, that would give you access to the inner core. How can you tell, though, whether that extrusion has gone down far enough to get you to the, do you know how long thick that layer needs to be?
Sure. So we would be happy, we would be joyous to just have a sample of the mantle, which is just below the crust. So it doesn't have to be too far down. Exactly where that is a very important question. Guiding that is the combination of impact simulations that try to replicate the size and the shape of this basin, and we are then trying to guess the impactor mass, the speed, and the orientation. And then those simulations will then predict where the material that's dredged up would tend to be. But also in combination, we must look to the remote sensing data on the moon, because there are regions of the moon that look compositionally different that have been postulated to potentially be this type of signature. So it's a combination of both of those areas of knowledge to do that.
Because we haven't explored the far side of the moon, do you think it would be a possibility that new elements could be discovered and then added to the periodic table?
Probably not, but it's the bottom of the periodic table are usually things that we've created in a laboratory, so we wouldn't expect to see new elements on the far side of the moon. But it's certainly possible that we would see new or different mineralogy. So not different elements, but different combinations of the way that rocks are put together. We probably know compositionally, but as I said, the remote sensing data of the moon does not indicate a completely uniform composition. There are definitely compositional differences that we think reflect both lunar processes, possible exogenic contamination, and maybe the interior of the deeper portions of the moon.
I'm wondering, how likely do you think that in the coming years or decades we will be able to say, because of trips to the moon and samples and other forms of data, that we are certain or nearly certain about like how the moon formed, or whether you think that there's so many variables and so many uncertainties that we will never really know for certain?
I actually think we're quite close. Based on what we understand now, for example, if you start to thinking about forming the moon any other way than a giant impact, because this general process of forming moons is so efficient, you have to then come up with a reason for how you got rid of the moons that would have formed from impacts before, perhaps. So that giant impacts form moons so well, I think tells us that that is the process that gave us the moon, and the fact that it explains the moon's bulk depletion in iron, which otherwise can be really difficult to explain. So it's really a matter of what's the type of impact, and why this is important to unravel is these are very different scale events. If we had two half-Earths colliding or a near fission event versus the canonical event, those tell us something different about the nature of Earth's assembly, and we hope to look to the moon to provide ground truths to those theoretical models on how planets form. And also, we hope that we can continue to develop predictive models for more other detailed aspects of the moon's composition, like its volatile content. So this is an extremely data-rich problem compared to those we usually work in astrophysics. So we are in the details, and we are trying to get everything to agree. But I would say the big picture is that we have a very good idea of the general type of event, and we're trying to figure out the specifics. And I do think we will get there.
The samples that we have from the mare, which I'm assuming already come from the mantle of the moon, have they been still isotopically identical to Earth or different?
In general, yes. So this is the plot on the right is some data where Canup et al. Have suggested that there's a bigger difference. So here, this BSE stands for the bulk silicate Earth. And so here is the bulk silicate Earth with uncertainty. And so to be exactly Earth-like, the moon points, which are the black circles, would be within this bar. And you can see they're speculating that as they are measuring samples that they think reflect greater depths of origin within the moon, that they're seeing greater isotopic variation. It's just the number of samples are limited, but yes, there is some evidence. So there's been arguments back and forth. Is the maximum difference between the Earth and moon, could it be 10 ppm? Could it be 20 ppm? But the difference is always of that order versus the 300 ppm difference between the Earth and moon and Mars. Okay.
Are other scientific communities in other parts of the world and other countries doing similar work or different work? And if so, is there any collaborative effort or transparency, or is it more of a competitive field and direction that you're going in?
Oh, we are absolutely always international in this type of modeling. Planetary science, it's very It's very rare for work on a topic to be exclusively done only within one country. So we are always attending conferences with international presentations. We often are directly writing papers with international colleagues, and certainly we are reading the papers written by anyone across the world when they relate to the topic we're working on. That's just kind of how our field works.
Thanks for the great talk. Do you think future isotopic signature data can tell us about the orbital parameters of the bodies before the impact, even before the gravitational focusing, like how tightly packed the system was?
Yeah. So the parameter space of potential impacts is multidimensional. So the main variables are the relative mass of the impactor compared to the target, the angle that it head-on, grazing, everything in between, and then the impact speed. And there's also pre-impact rotation, but we won't go there. So the impact velocity, it usually affects two main parameters in the outcome. If the impact speed is too high, which means that Theia had an orbit that was too different from the Earth before gravitational focusing. Okay? If the velocity gets too high, then instead of putting adequate mass to form the moon in orbit, too much ends up escaping. And so it is usually the case that the best outcomes are those that involve lower velocity impacts. In other words, a Theia that was on a more Earth-like orbit, which also seemed to be consistent with the idea that Theia would have been isotopically Earth-like. And so that was really the accepted solution for a long time until we learned that the Earth and Moon have the same tungsten isotopic composition, and that was the real fly in the ointment for that explanation. So the impact velocity is more tied to what's needed to produce a moon as big as ours rather than the isotopic signature, I would say.
Okay, one last question. I have a question.
Yes.
You didn't talk about Venus or Mercury or any of the others, but without going into any detail, now we're thinking about giant impacts, and the Earth-Moon system is very, very special. What about Venus and Mercury? Do you think that they experienced something like this and that led to some of their interesting characteristics?
Absolutely, especially Venus. The planet formation model suggests that it should have undergone giant impacts, and so actually the surprising thing is it doesn't have a moon. So we assume that it did have a moon, or at least that's my assumption, and that because of Venus's slow rotation, perhaps it tidally evolved inward and was lost. Perhaps it had a moon and there was a secondary impact that affected the rotation of Venus. There have been lots of ideas like that to explain how Venus would have lost its moon. It's a somewhat unconstrained problem. But yes, we think that these objects would have tended to have moons when they were forming.
Okay, for the next gen, practice up on your computer simulation skills, and this is a good problem for you to take on. Before we let Robin go, we'd like to present her with a few gifts, an appreciation for a wonderful lecture. This one is from the McDonnell Center for the Space Sciences, and then we have some personalized stationery for you, giant impact stationery.
Look at this.
And
awesome.
And this is a moon-scented candle of some sort. I don't know what that smells like, gunpowder or what? Okay.
Wonderful.
We've had a wonderful lecture tonight, very thought-provoking, and bringing us right up to date with the current thinking about this fantastic theory of the origin of the moon. Let's thank Dr. Canup again.
Thank you.
One more time.
Thank you so much.